A pleasant day to everyone. I am Dr. Bernardo Lejano, and I am honored to be a presenter in this session of DLSU Research Congress 2022. Together with my student advisees, Alyssa Cuevo, Diego Magpayo, Ritik Nihalani, and Emilio Tumbocon, we will present our paper entitled Utilization of Natural Cotton Waste Fiber in Concrete, investigating the optimal fiber length and amount based on split tensile and compressive behavior. Before I begin the presentation, I would like to take this opportunity to commend my students for working very hard in overcoming the different difficulties in doing the experimental test to complete this research, especially with the pandemic in our midst. For the introduction of this study, let me present the background, problem statement, and the objectives. Research shows that the amount of solid waste produced is rapidly increasing. In the Philippines alone, the solid waste currently produced is 40,000 tons per day, and it is estimated that by 2025, it will increase to 77,000 tons per day. A study by DENR showed that the textile waste is a significant contributor to the total amount of waste. This includes cotton waste. The construction industry is also a major contributor to pollution, producing 39% of the world's CO2 emissions. And this pollution is expected to increase as more land develops. In response to this, innovative and environmental friendly materials are being developed with two goals in mind. One, to improve the performance, and second, to reduce the amount of pollution generated in production. One of these innovations is the introduction of waste fibers in concrete. Cotton fiber reinforced concrete in particular showed potential in the few existing studies on the topic. In light of this, we decided to investigate the performance of cotton waste fiber reinforced concrete. So, in order to address the problem of waste and pollution generated by construction, cotton waste fibers is researched to find out if it can be proven as a reliable construction material, as this would greatly reduce the amount of cotton waste. The main objective of this study is to analyze the use of cotton waste fibers as reinforcement in conventional concrete. The specific objectives of this study are as follows. One, to evaluate the workability of varying amounts of waste cotton in concrete. Two, to evaluate the compressive strength of varying lengths of cotton waste fiber in concrete with a target compressive strength of 21 megapascal. Three, to evaluate the splitting tensile strength of varying lengths of cotton waste fibers in concrete. And four, to conduct a cost analysis comparing waste cotton fiber reinforced concrete to conventional concrete to find the more economical material. To give credit to my students, I am turning over to them the rest of the presentation.
As for the next part, here's where the review of related literature will be discussed. A table summary of the parameters and the related literatures chosen was created to see the types of fiber used, the fiber amount considered, and the fiber length chosen across all the studies. It is seen that the material is used varies. Fiber materials used in the related literature are polypropylene, cotton, nylon, wool, jute, and oil palm fibers. As for the fiber amounts considered, the amount seen is to be based from cement weight, concrete weight, volume of batch, and can vary from 0.0% to 1.5% depending on the study. Across all the literature, specific fiber lengths were studied as well, ranging from 10 mm to 57 mm depending on the study. It is to be noted that the related literature regarding cotton fibers does not consider varying fiber lengths.
For our research methodology and design, the research method involves analyzing how waste cotton fibers affect the strength properties of concrete through the use of the ASTM standard testing methods. The independent variables include the water to cement ratio, length of fibers, and amount of fibers, and these variables will be checked if it affects the testing properties of cotton reinforced concrete. Finally, a cost analysis will be conducted to determine the cost effectiveness of different concrete samples versus the control samples. There are two stages to the experimental method, the first being the workability test to determine the samples to be used for the second stage, which includes the compressive and split tensile strength test. The dimensions of the concrete samples for both the compressive and split tensile strength test will make use of 150 millimeters in diameter and 300 millimeters in height. Now, as previously mentioned, these are the independent variables, and in order to test the effect of these variables on the strength properties of concrete, a control of conventional concrete will be made. Now, for stage one, this involves the workability test. As shown in the table, the samples are categorized by the water to cement ratio, amount of cotton, and cotton length. For stage one, there are 20 cases to be tested as seen in the previous table. For each case, 2 trials were conducted per case, which overall resulted in 40 total trials for stage one. Stage one determines the water to cement ratio to be used for stage two. Now, for stage two, each case refers to the chosen water to cement ratio of the previous stage. Now, as seen for each case, a compressive strength test and a split tensile strength test is required. Now, from the previous table, there are 4 cases per strength test, and 5 trials were conducted for each case, which totaled to 40 total trials for stage 2. For the preparation of cotton, the cotton used for the experiment was already treated using mercerization, which increases the fiber's strength, shrinkage resistance, luster, and surface area of cotton. Mercerization involves immersing the cotton fibers in a sodium hydroxide solution of 30%. Now, for the summary of procedures, start with the preparation of cotton, mixing of concrete, transferring the mix to industrial pails to distribute the fibers evenly, conducting the slump test, and then the preparation and curing of cylindrical concrete samples. After that, the samples were then placed in a compression test and a split tensile test. For our results and discussion, the first set of results include the results from the workability test. The data that were gathered were the slump and the slump characteristics, and the table above shows the results for the water to cement ratio of 0.5 with varying amounts of cotton fiber. Now, for the second set of results are the workability results of the water to cement ratio of 0.6 with varying amounts of cotton and fiber lengths. For each case, based on the independent variables, 2 trials were conducted and the average was obtained. Now, based on the results, it can be observed that the higher water to cement ratio yields a higher workability, and that the increase in the ratio of water in the mix resulted in an increase in the workability. It can also be observed that the workability decreases as more cotton is added into the mix, and there is a steeper decline in workability for longer cotton fibers as more cotton is added. Based on the graph, the 0.6% amount of cotton yielded the best results when it comes to achieving the target slump. Therefore, this was used for stage 2. And as for the water to cement ratios, the 0.6 water to cement ratio was adopted for the concrete cylinders for stage 2, as this showed the higher workability.
As for the compressive test results, the samples were tested in Aztec Materials Testing Corporation in the Cavite laboratory location. Outliers were taken out, and the average compressive strength is adjusted accordingly. From the control to the 50 mm samples, it is seen that the adjusted average compressive strengths are 20.71, 20.58, 21.04, and 20.41 MPa respectively. To further visualize the differences in the strength, here is a graph that shows the comparison of the 4 cases. The results show that the use of 30 mm cotton fibers yielded the highest compressive strength, while the use of 50 mm yielded the lowest. Though the differences between the cases are minor, it is to be noted that 30 mm case reached the 21 MPa target of the study. Here is a summary of the fracture patterns that were taken from the results given by the lab. Type 3 fracture patterns is abundant between all samples, and type 5 fractures were also present. It is to be noted that 4 out of 5 samples in the control case practiced type 5 failure, and type 5 failures were also seen once in the 10 mm case and the 50 mm case. As for the split tensile test results, the samples were tested in the DLSU STRC structural laboratory. Outliers were taken out and the average split tensile strength was adjusted accordingly. It is seen that the adjusted strengths are 9.29, 8.55, 11.69, and 12.91 MPa respectively from the control to the 50 mm. To further visualize the differences in strength, here's a figure that shows a comparison between the four cases. The results show that the use of 50 mm cotton fibers yielded the highest split tensile strength, while the use of 10 mm yielded the lowest. It is to be noted that the 10 mm fibers do not benefit in the split tensile strength of concrete, while longer fiber lengths prove to have an adequate increase of split tensile strength, with 50 mm being the highest.
In our cost analysis, the main comparison will come from the amount of cotton fiber treatment used in the concrete mix for every cubic meter. Since the concrete materials will have the same volume of concrete mix for every fiber length variation and control samples, the only deciding factor for a cost difference will come from the cotton fiber treatment, assuming that the cotton fiber to be treated is waste. We can observe in the table that a comparison of the prices were shown per control, 10 mm, 30 mm, and 50 mm concrete samples. In terms of the cotton fiber treatment, it was mentioned earlier that the cotton fibers were purchased having it already undergone the mercerization process. To be able to give an accurate cost comparison for the treated fibers, the treatment process had to be analyzed in terms of cost that comprises of sodium hydroxide and water. So looking at the total cost, the addition of the treated cotton fibers in the mix results in a 1.34% price increase, that is 47.12 pesos, compared to a control sample. And having done the cost effectivity, it was observed for compressive strength that 30 mm is the most cost effective, having it to be lower than the control. And in terms of the split tensile strength, 30 mm and 50 mm were found to be the most cost effective, having it to be lower than the control.
Next, we have conclusion. Based on the results of the slump test, the addition of longer cotton fibers and the increase of the amount of cotton fibers used resulted in a decrease in workability. Aside from this, the results showed that the workability values of the 0.6 water to cement ratio concrete mix was higher compared to the workability values of the 0.5 water to cement ratio. The results of the compressive test showed that the 30 mm concrete samples had the highest strength out of all the other specimens. The control specimens had higher strength than the 10 mm samples and the 50 mm samples. However, the strength did not vary widely, seeing that the percent disparity of all the samples to the control are less than 2%. Therefore, the addition of fibers and varying length of fibers do not significantly affect the compressive strength of concrete. The results of the split tensile tests show a more significant disparity between the specimens. The 50 mm samples had the highest strength, followed by the 30 mm samples. The average strength of each of the two specimens were higher than that of the control specimen. However, the 10 mm samples had the lowest average strength. Therefore, the trend seen is that longer fibers will contribute greater split tensile strength, and concrete with fibers that are too short will be weaker than traditional concrete. Since the difference in compressive strengths are minor, workability and split tensile strengths are the main metrics of comparison. The results show that 50 mm concrete has the highest tensile strength but is less workable as fresh concrete and has the lowest compressive strength. On the other hand, the 30 mm concrete is more workable and has the highest compressive strength, but has less tensile strength than the 50 mm concrete. Overall, the 30 mm concrete has significant advantages over traditional concrete.
So again, this research is about the utilization of natural cotton waste fiber in concrete, investigating the optimal fiber length and amount based on split tensile and compressive behavior. Hopefully, this research would contribute to the reduction of waste and enhancing the properties of concrete that we use in construction. That's the end of our presentation. Thank you for listening.